Day. Any questions? I know a few folks weren't here the other day, so just a quick recap. You're allowed to bring one sheet of handwritten notes, both sides, 8.5 by 11, standard. I will collect them, you'll get them back, so just make sure you have your name on them. You can expect 2 working problems on the exam, equal weight. All right.
And that's it? No, like, conceptual questions?
Right, there may be some conceptual question
working
built
problem.
into it, but yeah, pretty much 2 working problems. You can, be prepared to, some of these problems may encompass multiple concepts and lectures, so be prepared for anything along those lines, right? And it's through lecture 8, so the beam on elastic foundation stuff, no finite element analysis. All right, so we'll continue on with finite element discussion. Last time we stopped kind of just shy of finishing this example of an indeterminate beam. And I was talking about how the solution is easier if it's indeterminate because then you have more known displacements going in, which means that your first partition matrix shrinks down quite a bit, and you can readily solve for those displacements and then find all of your unknown forces. So to wrap up this example then, we have found the forces. So now the next step is to interpret those results onto a sketch, essentially your final free body diagram. So go ahead and sketch that out here. And when we're interpreting these results, we still have to stick with the finite element sign convention, right? So we have positive 3m over 2l reaction at the left end. M1 over L was given as M0 over 2L. At this point, we're going to take that L back to the other side, so we will have appropriate units attached to our moment. And since it was given as a positive result, right, we interpret that according to the finite element sign convention as counterclockwise. And that would be M0 over 2. We have the applied load, which was M0 in the positive direction on the right end. And then our reaction force, 3m0 over 2L in the negative direction. So now that we have appropriately applied our results according to the finite element sign convention, now we can step out of the finite element analysis, apply our regular mechanics sign convention, which we know means a negative moment at the left end, right, for counterclockwise. So positive result, finite element analysis, interpret that as counterclockwise. Step out of finite element analysis, negative moment if you were to draw shear moment diagrams and things like that. Verify that equilibrium is satisfied, so summing forces in Y is equal to 0. Visually, right, that's sufficient. We can just say yes, that works out. Summing moments about a point. Go ahead and show the equation because it's not as obvious. In some cases it is, but I always like to see this written out to verify. So we've got our moment at the left end minus, so I'm summing moments about node 2, all right? So we got the moment at the left end minus the reaction at the left end times its moment arm. Plus the applied moment at the right end is equal to 0, and that does check out. Now we can use our displacement results to plug it into that generalized deflection equation. All right, so we've got v of x is equal to, after eliminating all the terms associated with the zero displacements, and since we have 3 of those, we're just left with 1 term from that generalized expression, all right, times the value that we found for theta 2L. So once we plug everything in, we get negative m naught L squared over 4EI times, in parentheses, x squared over L squared I wrote it wrong, x squared over L squared minus x cubed over L cubed. All right, questions? All right. So now a few more notes on boundary conditions. The first 3 are what we're most familiar and comfortable with, right? Of course, we have for a roller support or a pin support in those conditions, boundary condition for beam behavior is the deflection at that node is equal to 0, but we don't know the rotation. All right, so that would be for a pin or a horizontal roller. If we had a fixed or a clamped end, then we don't know either of those possible displacements, right? Or what am I saying? We do know them, right? They're both 0. For the free end, we don't know either. And then there's a 4th one, or 5th one, I guess, that you may encounter, which is what we call a sliding clamp. So this is a scenario where vertical displacement would be allowed, but rotation is not allowed. So in that case, we would not know the vertical displacement, but we do know theta 2 is equal to 0.
Physically, what would a sliding clamp?
So that's a great question. I'll try and see if I can find some images to show you. I haven't actually ever designed anything like that myself, but yeah, essentially it could be something like, you know, you've got something attached rigidly to a surface, you know, a supporting surface like that, that would prevent rotation. So it would be kind of continuous to that surface, but then it would be allowed to translate in this direction along a rail or something.
Like vertical, long slotted holes?
Similar, but yeah, but you'd have to add something to prevent rotation. Because vertical long slotted holes, what you're thinking of, what I think you're thinking of, that would most likely allow rotation, right? Unless there was something strengthening that. Yeah. All right, so now we are going to expand on this and bring more elements into the picture. The reason for adding elements, adding nodes, and finite element analysis is to refine the system, right? And as I mentioned earlier, there's a balance to be had. So the more refined your analysis is, your model is, the more accurate it will be. However, that takes more power, more time to process. It's more expensive. So try to find a balance. So at a minimum, where do we need to have nodes? Well, we need to have nodes anytime we have a support or at any location where there could potentially be a applied load or moment. Generally, I guess technically, and depending on the program, you may not need to have a node there when you are developing your model, but the program will remesh it so that there is a node there. And also at any location where you might want to extract an exact displacement or rotation value, right? So I'll just note here that a node is needed for supports and every point with a possible applied force or moment or desired displacement value. All right, so general setup, typically number nodes left to right. All right, so we've got element numbers noted in the box, node numbers in a circle, and this rule of numbering nodes left to right, it's really mainly applicable to beams. Once you get into frames, it can get a little bit more complicated, but generally speaking, it's helpful to stick to that trend. All right, so, quick just allocation of the degrees of freedom here, right? At each node, we've got 2 degrees of freedom, which is transverse displacement and then rotation. Normalized to have consistent units between the two. And then for forces, all right, you'd have a force at each node, but where we have a node that connects 2 members, all right, technically there is a force at node 2 in element 1 and a force at node 2 within element 2. So I'm numbering those separately as F21 and F22. Those are internal forces or member end forces. The nodal force, F2, is going to be the sum of those. All right, and it's similar for moments. I'm not going to draw all of that notation out for clarity, but we also have moments. I'll just note, right, similar for moment. All right, so expanded process, you would technically have a matrix equation for each individual element, right? And that's coming from, remember, that generic matrix equation that we pulled. And I think, did I say somewhere in here, this is your starting point, right? Or maybe I just, oh yeah, right here, starting point. So this general matrix equation applies to every element. And trying to get back to, I'll just go the hard way or the long way. There we go. All right. So again, I like to label the columns and rows according to the nodes that are associated with them at the very least. So the first node is associated with the first two columns of element 1 and the first two rows of element 1. All right, second node is associated with the second two columns of element 1 and the second two rows of element 1. So you can split it up like this. Similarly, for element 2, 3, we have node 2, node 3, dividing up the columns, and then also 2 and 3 for the rows. So for the overlay, right, when we combine them to obtain the equation for the whole system, which is at this point just consisting of these two elements, we're going to look at the nodes that show up in both elements, which in this case is just node 2. So looking at the node 2 columns and rows, pull those values, right? So that's those 2 by 2 quadrants that I just highlighted. Those are going to be placed in the node 2 column and row of the overlay. So I'm going to label our overlaid matrix. We have node 1, node 2, node 3. For the columns, node 1, node 2, node 3 for the rows. Overlay will be in the node 2 columns and rows. So we have 12 plus 12, negative 6 plus 6, negative 6 plus 6, and 4 plus 4. All of these other values that I wrote in here, which if you caught the updated version of these skeleton notes, you should have them too. I posted them Wednesday after class. Otherwise, you can fill them in later. These values all just come straight from dropping the associated row, column, quadrant, and mapping it in here, right? So that's where those come from. And then the remaining quadrants in the overlaid matrix will just consist of zeros because there is no element connecting node 3 and node 1. So any value that has that combination in your overlaid matrix will be 0 there. Yes?
on column 3, the second row, I believe, the bottom 6 should be a negative.
This one here?
No, not one.
Oh, this one here.
Yeah, right, negative 12, 6, negative 6, 2.
Yes, good catch. Thank you.
The 12 below that should be positive.
Yeah.
Good catch. All right, thank you. So that's corrected those values. Yep, that's right, because those are coming from right here. All right. So just comment on here that we have, I'm gonna go ahead and highlight this box. And since those corrections were also highlighted, I'm just gonna change the color. To avoid confusion with the rest. So this, I'll just note, right, we've added the stiffness values. At common nodes. And then alluding to what I sketched up above, the force F2 is technically equal to the end member force F21 plus the end member force F22. And M2 similarly is M21 plus M22. So if you were to evaluate those elements individually, like in the individual matrices here, all right, so this would technically be M21 and F21 in here, and this would be F21 and M2, or excuse me, F22 over here and M22. So this note is forces from left side of the common node. So next we'll consider a simply supported beam with a point load at a center, modeled with two elements. And so here we're told that the beam stiffness properties are constant along the whole length of the beam, which is helpful. And we got to number our nodes, so we'll do that left to right. And again, I like to label the matrix equation. And notice that I started with that general overlaid equation, all right? So this right here, I'm gonna add a note here. This can be your starting point for any two-element beam. with the caveat that EI and L should all be the same, or at least this ratio of EI over L cubed should all be the same. All right, so if you have individual element matrices that have different EI or L values, then that's going to affect what your overlay looks like and the rest of the matrix. But in this class, this will always be the case. So in this class, you can use this as your starting point.
If they weren't constant, would you just adjust one of them by like a factor so that the I over L is the same?
Yeah, exactly.
Okay.
Yeah, so you would just normalize the value out front so that you can add them together and just have EI over L cubed out front, and you just have some different values showing up in one or both of them.
Okay.
Yeah. So, all right, so back to this example then. I'm going to label the columns here. So we have our columns associated with displacements in order. And imposing boundary conditions, all right, we have a simply supported beam, so V1 is 0 and V3 is 0. That's all we can say for this problem. But that allows us to eliminate the columns associated with those two displacements. So that means we have 4 rows of known forces, all right? So we'll go ahead and apply that. Wherever we don't know a displacement, we have to know the force. So at node 1, there's no applied moment, so M1 over L is 0. At node 2, F is equal to negative P, and M is equal to 0. And at node 3, no applied moment, so M is 0. Those are the 4 rows that we start with for our first partition. So we'll have EI over L cubed out front. And then in the first column, 4, negative 6, 2, and 0. So to help with this, I'm just going to highlight the rows that we're using. Second column, negative 6, 24, 0, 6. Third column, 2, 0, 8, 2. Fourth column, 0, 6, 2, 4. Bringing the labels back. We have theta 1L, V2, theta 2L, and V3. And those are the displacements that go in our displacement vector as well. Oh, mistakenly wrote V3 above row 4, it should be, or column 4, it should be theta 3L. Set that equal to our known forces, which is 0, negative P, 0, and 0. So here, quick gut check. Our stiffness matrix is square and symmetric. All right, so it always has to be square for the first partition solution to work. So we're going to pre-multiply both sides by the inverse. to get the result for our unknown displacements. And we obtain through that solution theta 1L, V2, theta 2L, and theta 3L equal to negative PL cubed over EI times 1/4, 1/6, 0, and negative 1/4. So we're going to use that for partition 2. All right, and if we were going to just interpret our final answers, right, we would say theta 1L is equal to negative PL, let's see. At this point, we would just want theta 1, not theta 1L, right? So that's equal to negative PL squared over 4EI, and so on. All right, so second partition, the two remaining equations are shown here. Again, just using the 4 rows that are not multiplied by our original 0 displacements. Now we do have a result of 0, right? So theta 2L is 0 in this solution. So at this point, you could go ahead and say, well, that's equal to 0. We can get rid of that column, right? And then work your way through. But essentially what you want to do is plug in the results from the first partition. And you'll end up with F1 and F3 equal to P times 1/2 and 1/2. Now, intuitively, we probably already figured that out as soon as we set eyes on this problem, right? But it's important to still treat those as unknowns through the duration of this process. Otherwise, you won't be able to solve for those unknown displacements. And then what we would do is use the equilibrium to verify the results, right? So that's, again, an easy thing to identify the reactions for determinate problems, but when you get to indeterminate problems, you can't do that. So it's important to just get into the habit of treating all reactions as unknowns throughout the solution until the very end. So we got final free body diagram. All right. Eyeballing it, yes, equilibrium checks out. Sketching the deflected shape using the results, right? We can probably all sketch the deflected shape just intuitively, but we want to make sure that our results make sense. So we have theta 1 and theta 3 are equal in magnitude, right, and opposite in direction. So we have a negative value for theta 1 and a positive value for theta 3. Negative translates to clockwise rotation. Positive translates to counterclockwise. So that checks out with a deflected shape like this. At node 2, theta is equal to 0, so that also makes sense, right? And the deflected position of node 2 was given as negative value, right? Negative PL cubed over 6EI, so that also makes sense. And so then the deflection equation for this guy now that we have two elements, we have to pick and choose which element to write the deflection equation for, or do them all. In this case, I'm just going to demonstrate the one for element 2. Because that 4-term equation that we derived in previous lecture for generalized deflection, that's for just a single element, all right? So we can't apply it to the whole beam. We have to apply it to individual elements. So we'll have v of x for element 2 would be equal to, in parentheses, the term is 1 minus 3x squared over L squared plus 2x cubed over L cubed times V2. And then I'm going to just skip theta 2L and V3 since they're equal to 0. So that would leave us with x squared over L squared minus x cubed over L cubed times theta 3L. And that can be simplified to negative P over 12EI once we plug in our values for V2 and theta 3L times 2L cubed minus 3x squared L plus x cubed. Just a more user-friendly version. Questions so far?
Where are those deflection equations again?
So it's in like the 3rd or 4th page in from the start of the finite element. Third page in, yeah. Yeah, that's where the full equation is. All right, so now this next example is pretty interesting. This considers the scenario where you have a known displacement that's not 0. All right, so beam bending from impressed displacement or imposed displacement is usually how we say it. Here we have a cantilever beam and we're forcing the free end into a vertical displacement of 1 inch in the positive direction. We got 2 elements to represent this beam. We're looking for all the unknowns in the problem. So the unknowns include the reactions at node 1, the displacement and rotation at node 2, the rotation at node 3, and also the vertical force that would correspond to such a displacement, right? So here we've got our starting point, right? The 6x6 overlaid matrix equation. I'm going to go ahead and impose boundary conditions. So V1 is 0, theta 1 is 0, and we know V3 is equal to 1. We don't know the rest of those displacements. Wherever we don't know a displacement, that means we know a force. So at node 2, what is F2? There's no applied force, so that's equal to 0. Same with the moment. At node 3, we don't know F3, all right? So this is an unknown. The moment is equal to 0 at node 3 because there's no applied moment. Labeling these columns, all right, we got V1, which is 0. You can eliminate column 1. Theta 1L, 0, eliminate column 2. V2, theta 2L, V3 is equal to 1, but we can't eliminate that column, right, because it's not multiplied by 0, it's multiplied by 1. So we have to get a little creative. And then we have theta 3L. All right. So looking at this, we have 3 rows with known forces. All right, so our first partition will be the first 3 rows. Let's just write it out. Exactly. It's not going to be square. Rut row. So our V2 column is 24, 0, and 6. And I'll go ahead and highlight those rows. Theta 2L column, 0, 8, and 2. Our V3 column, which is equal to 1, negative 12, negative 6, and negative 6. Theta 3L column is 6, 2, and 4. So this gets multiplied by our displacement vector with 4 rows in it, V2, theta 2L, 1, and theta 3L. And that's equal to a bunch of zeros. So what do? You can't take the inverse. How do we solve this?
Why don't we just include the other row? And then we have 4, we just create the same.
So if we include the other row, though, then we have an unknown over here. Right? But you're kind of on the right track of manipulating the number of, or the dimensions of this matrix, right? What we can do is we can move this column to the other side of the equation, right? So we move the known column to the right-hand side.
So should that 1 be there? It should be in the displacement.
After we move the column, no. Yeah, so once we move the column to the other side, then this can go away. Because this is tied to that column, right? Yeah. So I'll write the new version of our equation here. We got V2, it's 24, 0, 6. Theta 2L, 0, 8, 2. And then theta 3L, 6, 2, 4. So now we have a square matrix. We have 3 unknown displacements. And then our right-hand side will be our original matrix of known forces plus EI over L cubed times 12, 6, and 6. All right, so now we can go ahead and solve that. Applying the same method of taking the inverse and pre-multiplying both sides. Where now the right-hand side just includes this. So then we would get results of 0.3125 for V2, 0.5625 for theta 2L, and 0.7500 for theta 3L. These results would be in inches. So all the EI and L values cancel out in this solution because the known value, the imposed displacement, was given as a number. So our results will be in terms of the known value for displacements. Now that we have those displacements in inches, we can plug them into the second partition, and our forces would then be in terms of EI and L, right? So we don't have time to finish that, but we'll wrap that up next time on Monday, interpret all the results, and then we'll move on to tackling distributed loads. Yeah. Yes?
That constant isn't one, we have to go through and multiply.
Sorry, say that again. If
So like B3 is 1 in this case?
Yep.
So all we did was just multiply through by 1.
That's correct, yeah. So if this was 2, then your right-hand side would be, multiplied by 2.
And that's how you get rid of that constant. But I guess the one that we got rid of
Here?
in that vertical,
Mhm.
that's a different number.
No. So this is the same as this, right?
So
Yeah.
if that's like a 2
Oh, yeah, if this is a 2,
crossed out, because we have incorporated into the right side of our equation.
yeah, exactly. By moving the right side over and multiplying, right, in moving the right side over, you are multiplying it by this value and then moving it over is really what you're doing. And so then, you get rid of it in that vector. Yeah. All right, other questions? All right, well, have a great weekend, everybody. See you Monday.
Those